Gracias a todos, bienvenidos. Hoy es la primera charla del Festival de la Astronomía con la que iniciamos. No vimos una mejor manera de iniciar con el padrino, precisamente, Kelly Beatty. Kelly Beatty, como saben ustedes, es editor en jefe de la revista Sky and Telescope, probablemente la revista más prestigiosa de divulgación de la astronomía en el mundo. Y hoy tenemos el honor que venga a compartirnos una charla por demás interesante. Kelly nos va a platicar acerca de actualmente qué líneas de investigación y de exploración se llevan para encontrar la posibilidad de vida fuera del planeta Tierra, así como lo estás escuchando, tanto en planetas cercanos en el sistema solar que habitamos, como incluso más allá de esto. Pero sin mayor preámbulo, los dejo con la plática, que aclaro, aunque la plática sí va a ser en inglés, pero tuvimos a bien agregar los subtítulos ya en español, y una vez terminada la charla, les agradeceremos compartir con nosotros algunos comentarios o preguntas que tengan para Kelly, y con mucho gusto haré la labor de traducírselas para que él nos acompañe con sus respuestas, ¿de acuerdo? Muchas gracias de nuevo y bienvenidos. Voy entonces a compartir. Sorry, Kelly, would you like to say some words to our audience? Kelly, ¿te gustaría mencionar algunas palabras para nuestra audiencia, por favor?
I am grateful that you are all here watching and that you all have an interest in astronomy. It is
Kelly menciona que está muy agradecido de que todos ustedes estén observando la charla y del interés que manifiesten en la astronomía.
In some ways, it is the first science of humankind because our ancestors looked up into the night sky and wondered what it all meant, and we are still trying to figure that out.
Kelly menciona que de hecho la astronomía es la primera ciencia de nuestros ancestros porque solamente requería mirar al cielo y maravillarse de qué es lo que está ahí. Entonces, Kelly, you were saying?
And one of the questions that we have asked for a very long time is, are we the only ones in this universe? And that's what my talk will address.
Y una de las preguntas precisamente que nos hemos hecho es, ¿realmente somos los únicos en el universo? Y precisamente la respuesta a esa pregunta es de lo que trata la charla que hoy Kelly Beatty nos comparte. Thank you very much, Kelly. Recording.
Hello, everyone. My name is Kelly Beatty, and tonight we're going to be talking about whether we are alone in the universe, how we are seeking life in other places, and how we hope to find it someday. But before we do that, I want to give you a little bit of a foundation. This is a picture of not a star in the nighttime sky. This is the Earth as seen from the surface of Mars. And this is a quote from a famous book called The Martian Chronicles by the author Ray Bradbury. And he asks, the wife asks on Mars, do you ever wonder if there's life on the third planet? That would be Earth. And her husband says, these are Martians, the third life is incapable of supporting life. Our scientists have said that there's far too much oxygen in their atmosphere. And when you think about it, we are used to the life here on Earth, but we don't know whether life elsewhere will need oxygen or carbon dioxide or what. So let's start with talking a little bit about life and how we define life. We define life as a way to, there we go, a condition that distinguishes animals and plants from inorganic matter. Life has the capacity for growth, reproduction, function, activity, and continual change preceding death. So that's a pretty broad definition. One of the things that I often hear is that, oh, there must be life because there is so much organic matter in the universe. And organic matter is not life. These are different simple organic molecules in our everyday world. Most of you are familiar with methane or natural gas, benzene, even amino acids. They are interesting organic molecules, but they are not life. And so let's talk about the conditions that we need for life. As far as we know, water is essential for life. Water is an amazing molecule. It has the ability to dissolve many things. And it's a special kind of molecule with a kind of polarization to it. It's not symmetric in charge, and so it has many interesting properties. It's also true that, as far as we know, carbon is essential for life. Carbon can make many different bonds with other chemicals. Now, there's been a suggestion in the past that maybe silicon, the atom silicon, can substitute for carbon, and maybe there can be silicon-based life. And I'm showing you here a funny picture from a Star Trek episode in which Captain Kirk confronts a creature called the Horta, which is based on silicon. But now we realize that silicon is not a very good substitute for carbon. The kinds of molecules that we can make with carbon, we can't make with silicon. So we think that it's carbon or nothing. Now, a lot of people think that sunlight is essential for life. So much of our everyday existence depends on that sunlight for photosynthesis, for giving us energy, but it turns out that's not the case. There are many different kinds of microbes, small organisms, that can live without sunlight. They live in the deep ocean. They can also live at extremely high and low temperatures, or in conditions that are either acidic or alkaline. And even intense radiation, life can survive in amazing places. This is a photograph of some worms on the bottom of the Gulf of Mexico. And the worms are feeding on the white deposit that you see there, which is called methane hydrate. And the worms feed on bacteria that use this methane hydrate for food. So life can survive in amazing ways. I mentioned radiation. This is what happens when you take a laboratory beaker made of Pyrex and subject it to intense radiation from gamma rays. And yet it turns out that there is a type of bacteria, you can see the name of it there, that if you expose it to the same amount of gamma ray radiation, it continues to live and even thrive. Now, I hope this comes through. This is a little video from the Atacama Desert in Chile at an altitude of about 14,000 feet. That's roughly 4,000 meters. And I want to show you a little stop. You can see the boiling there. And I want you to pay attention to the red stains around the red stains. The colony of bacteria that live in that boiling water, that they can survive in boiling water. And the last example of a really extreme organism is what we call a tardigrade. This is a very small creature. It's both ugly and cute at the same time. It's been on the Earth for 600 million years. It has survived all kinds of extremes on Earth, and it can even live in space, in the vacuum of space. Interestingly, there was an Israeli spacecraft that took some samples of tardigrades to the moon in order to study them, but the spacecraft crashed and did not land successfully. So who knows? Maybe there are tardigrades running around loose on the moon right now. Okay, so how did we get life on Earth? That's our next big question. We know what life is. How did it get started here on the Earth? We have to start 4.5 billion years ago when our solar system formed. The sun formed in the center, and Earth and the other planets formed from a giant disk of gas and dust that surrounded the sun as it formed. These planets gradually came together, and even after the planets formed, there were still a lot of material left in the solar system, bits and pieces that did not get collected. And eventually, our Earth formed, not long after the sun. But you know, the early Earth was a very hot and dramatically dangerous place. Here's a little video that shows that. Imagine stuff raining down from space all the time. And our planet is so hot that it's and that big thing there, that's the moon. You know, when the moon first formed, it was much, much closer to the Earth than it is now. And it's gradually moved farther away over time. So if you can imagine how strong the tides in our oceans are now, imagine how much stronger the tides would be if the moon were 5 or 10 times closer as it was when our planet first formed. So eventually Earth became a nicer place. We cooled off, the oceans formed, our atmosphere settled down. There were still impacts occasionally, but it became a nicer place. And what was important in that early time is that the atmosphere of the Earth was nothing like what we have today. Our atmosphere at the beginning of our planet was mostly hydrogen and helium, just like the sun, just like the cloud that we condensed from. And the molecules, water, maybe methane and ammonia, but a lot of that early atmosphere no longer exists because it was blown away, driven away by the solar wind, by the sun's intense radiation. And it was replaced maybe by 3 billion years ago with the basics of the atmosphere that we have today. Nitrogen, mostly, and a little bit of carbon dioxide, some water vapor. One of the things that's missing in that list is oxygen. Oxygen wasn't in our early atmosphere. That's because whatever oxygen existed combined with the rocks. There's a lot of oxygen in everyday rocks. And it wasn't really until about more than 2 billion years after Earth formed, and the first microbes started changing carbon dioxide to oxygen, that our atmosphere began to accumulate the oxygen that we have in it today. So that transition was really important, and it set the stage for the kinds of life that we have on our planet today. Now, that formation doesn't really answer the question of where Earth got the water that it has today. You know, think about it. Our planet is covered about 75% by water. There's less land than there is ocean. Here's a picture of the Earth taken by an Apollo astronaut. You can see all the water. Now, if I strip away all that water and bring it together all in one big ball, and I put it on the surface of the Earth, this is what that would look like. If you took all the water in these oceans, in the Earth's oceans, which are very broad but actually not that deep, and we brought it together, that would be the large ball, that large droplet of water. That's all the water on the Earth right now. And if I expand on that, there are 3 balls there actually. So the big one is all the water on the Earth. And the medium ball is all of the fresh water that exists on Earth, both on the surface and underneath in what we call aquifers. And the little tiny droplet represents all of the water, fresh water, on the surface of the Earth right now. So as you can see, although we depend very heavily on water for life, Earth does not have as much water as you might think. And where did that water come from? I think most scientists would agree that Earth did not start off with that water, but it was delivered by some comets, because comets have water in them, but also with asteroids that are rich in water. And there are many of these out in the asteroid belt. They collide with the Earth and they release the water that they are carrying, and that becomes part of the water that we have today on our planet. There are a lot of other ways that water can conceivably be created on the Earth, including some chemical reactions, but almost certainly most of the water came from comets and asteroids. Okay, if we have water, and if we have sunlight, and we have a warm planet, and the right kind of atmosphere, how did life actually arise? Well, many scientists have spent a long time trying to answer this question, and they don't have the answer yet. But in 1952, 70 years ago, two scientists did a simple experiment. They took a beaker full of gas, you see it over here on the left, full of water and methane, ammonia, and hydrogen, the kinds of gases that would have existed early in Earth's history. And they applied a spark, an electrical spark, to simulate lightning. So if you can imagine the early Earth, there was a lot of lightning, and they watched to see what would happen. And what turns out is that after a very short period of time, a lot of the carbon in these simple molecules was converted to organic compounds and even amino acids. And so they thought that they had sort of answered the sort of formation. You take a simple mixture of gases, you apply energy to it, and you get these organic molecules, and eventually from them, life would form. And where? Well, the thinking was that maybe in shallow tidal pools at the margins of the oceans, these organic molecules could concentrate and eventually somehow, some way, come together in a way that was the first forms of life. But guess what? We now think that's not really what happened. We think instead that life got its start at the bottom of the ocean, because at the bottom of the ocean, think about it, early in Earth's history, we were still getting hit a lot by asteroids and comets. The surface of the Earth was a dangerous place. But down deep in the oceans, you would be protected from that. And this is a video of what is called a smoker at the bottom of the ocean. And you can see in the middle there, this is where water has circulated underneath the bottom of the floor of the ocean and is being ejected out at very high temperatures, full of nutrients because it's come in contact with hot rock underneath the ocean floor. And scientists have found that in these regions, in the ocean floor, they are teeming with life. There is so much life around these vents on the ocean floor. And so this perhaps is where on Earth life began. Now, when did it begin? It's hard to say. The earliest forms of life we don't have traces of anymore. There is a very controversial suggestion that there were some fossils found in Greenland that might be from life, in which case they would be 3.8 billion years old. Now that's important because that's only about 700 million years after the formation of the Earth, yes, but it was only about 100 million years after the intense rain of meteors, asteroids, and comets ended. So that would be a fairly brief time from the ending of that great bombardment until the beginning of life. But the places where we do know that life really did arise come from these funny shaped rocks, which are called stromatolites here in Australia. And they are essentially deposits that were made by colonies of algae, cyanobacteria, from about 3.5 billion years ago. You can see one of them here in this picture. And so these cyanobacteria, or what we now today would call blue-green algae, played a really important role. And that is, they were the first organisms on our planet to take carbon dioxide from the air and convert it into oxygen. And that is when the level of oxygen in our atmosphere started to rise. So here in one simple graphic is the history of life on Earth. Our planet was formed 4.5 billion years ago here. The first microbes probably arose about 1 billion years later. The cyanobacteria were very widely distributed about 2.1 billion years ago. Then came real plants, higher order life forms, aquatic life in the oceans, reptiles and amphibians, and then finally about 7 million years ago, which was not very long ago at all in the grand scheme, in this grand scheme, this grand history, humans arose on the Earth. Okay, so that's what we think is the background of the development of life on Earth. Now, what about life elsewhere in our universe? Let's start with our solar system. And when you think about places in the solar system that could be a place where life exists, most people will say, well, Mars is a very good candidate because Mars is, in some ways, a planet very much like the Earth. It has about half the diameter of the Earth, so it's smaller. Its gravity is not as strong. But if you think about it, the Earth has so much water on its surface. Mars actually has roughly the same amount of surface area as we have dry land on Earth. So that's very comparable. Also, Mars has a year which is only less than 800 days compared to our 365 days. It takes a longer time to circle the sun, but it spins in 24.7 hours, very much like the Earth does, almost exactly the same amount of time. And also like the Earth, Mars has seasons because its polar axis is tipped, and it has a lot of features on its surface that we think would be very much like the Earth. And so in the late 1800s, more than a century ago, astronomers, especially Percival Lowell and another one named Giovanni Schiaparelli, during a especially close passage of Mars near the Earth, used their giant telescopes to see what the finest details were that they could find on the surface. And both of them thought they saw very thin lines crisscrossing the surface of Mars. And they interpreted these to be lines that were, in Italian, the original word was canali. And I'm not sure what the equivalent word is in Spanish. I should figure that out. But it got translated to English as canals. And the difference is canali means a channel, like the English Channel. But canal is something that was artificially built, like the Panama Canal or the Erie Canal, made by somebody intentionally. And so the idea arose that Mars was inhabited by creatures that took the water from the polar caps of Mars, their frozen polar caps, and brought it to distributed around the planet. This is a painting from many years ago of what that might have looked like. Water from the melting polar caps being directed to the parched farms, if you will, of Mars. In fact, around in the year 1900, the French Academy of Sciences, this notion that life existed on Mars was so widespread, everybody believed it, that in 1900, the French Academy of Sciences offered this huge prize, this huge amount of money for anyone who could make contact with another civilization except Mars, because that was considered too easy. They figured that the Martians would be in touch with us all the time anyway. So when we kept studying Mars through our telescopes and not seeing all the detail we'd like to, and it wasn't until we started visiting Mars with spacecraft in the 1960s that we got to see what it was like up close. And if anyone had hoped to find life, they were very disappointed because Mars looked very much like the moon, at least what we saw in these early pictures. Very heavily cratered, nothing that looks very Earth-like at all. Now, one of the things that those early spacecraft discovered is this small feature here with the box around it, which this was discovered in 1976. And when it's enlarged, it has a remarkable appearance like a human face. So a group of people decided that this must have been intentional, that there must have been Martians, and they carved this giant rock to look like a human face. I don't know how they knew what humans looked like, but there is the face. And it was quite a controversial subject. But now we know that that face, which you see there at the lower right corner, is nothing more than a large hill that has been eroded in such a way that when the sunlight strikes it just right, at just the right angle, it has the depressions for an eye and cheekbones and so forth. But it wasn't carved. It's just a natural feature. But what is true is that later spacecraft showed us that Mars did have Earth-like features. There are places on Mars where giant rivers have flowed across the surface. They're dry now. There's no water on the surface of Mars now, but there was at one time, billions of years ago. And we do know that Mars has polar caps, just like Earth has polar caps, that consist of water ice and also frozen carbon dioxide, or dry ice. And we've been able to map using a technique that's a little complicated to explain, but we can tell just by studying Mars from orbit that there is a lot of water ice buried under the surface of Mars. And that water has to be very close to the top. It's not buried really deep, it's actually up very near the surface. And so our history of exploring Mars with landers has always in the back of scientists' minds, will we find life on Mars? This is the first lander on Mars that was successful, the Viking lander in 1976. And since then, we have had other landers and rovers. These are all NASA rovers. The big one right there is Curiosity, which has been on the surface for a very long time now. And Curiosity was dropped onto the surface of Mars inside a crater called Gale Crater. That's about 150 kilometers across, roughly. And it has a tall mountain in its center, and the white oval there shows you where Curiosity landed. And the reason that scientists wanted to go there is that tall mountain in the center is a stack of deposits, of sediments, very much like the Grand Canyon. And I don't know if any of you have been to the Grand Canyon. I hope you get to go someday. It's a wonderful place. And in the walls of the Grand Canyon, you can see layers just like this. And the oldest layers are at the bottom, and the youngest layers are at the top, just like on Mars. And so what Curiosity is designed to do is to travel up this slope among all these layers to try to determine what the composition of the layers is. Because what we know about Mars is that early in its history, Mars had a very pleasant climate, relatively speaking. It had an atmosphere that was neutral. The soil pH, the acidity was neutral. There was plenty of water on the surface. It was a pretty nice place. Its atmosphere was thicker. And then something happened to Mars that we don't understand. And later, in current times, in the last couple of billion years, Mars has become a very horrible, difficult place for life. It's very cold. There's a lot of radiation on its surface. The rock chemistry has changed to be much more acidic than it was before. And so we don't know what caused this change, but the little white line there is showing the path that Curiosity has been taking to go from these ancient clay deposits, which are the neutral ones early in Mars history, up the slope into these higher deposits that contain a lot of sulfur, not a very pleasant place for life at all. That process is ongoing. But we do know that somewhere along the line, Mars went through a dramatic change in its environment that made it more hostile for life. This is a picture of an ancient river on the surface of Mars that probably has not had water in it for 4 billion years. So our latest rover is called Perseverance. This is the NASA rover. And one of the things that it is going to do is, it's obviously been very successful. Many of you, I'm sure, have followed the Perseverance mission. There's also the little helicopter Ingenuity. But Perseverance is in the process of collecting samples from the surface of Mars, very carefully chosen. For example, here, you see these two holes in this rock. Perseverance has drilled holes into the rock, and then it takes the dust that is generated by drilling and collects it and puts it in a little tube about the size of your pinky finger. And it's got dozens of these little samples that it's collecting and storing. Perseverance is going to put all those samples in a specific place on Mars, and then someday, maybe a decade from now, another spacecraft will land where those samples are, pick them up, and bring them back to Earth so that we can sample them and study them and find out everything that's about them in our laboratories here on Earth. This is important because Perseverance has found that in some of the samples that it has taken, there are organic molecules, which is unusual because they should all be destroyed in the harsh environment there. So we don't know what will wait for us when we get those samples back. Maybe we'll get them and find out exactly what's going on. Now, it's landed in this crater called Jezero, and this is what the crater looks like. It's this big, round, circular object here. It's about maybe 60 kilometers across. And you can see right here, there is a river that has cut through the rim of the crater and made this big, broad deposit on the floor. So whatever the river was carrying, sediments and maybe clays and other, maybe some organic molecules, has become a deposit here on the floor. You see it with all these little fingers. And so Perseverance has landed here, and its job is to go into these sediments and try to collect the samples that are most likely to contain evidence of past life. One of the things I want to say right now is that you, I'm sure, hear all about NASA's missions. We in the United States hear all about NASA's missions. And guess what? NASA is not the only country in the world that is launching spacecraft to Mars. The Chinese have launched a lander and a rover. You see an artist picture of it there. Tianwen-1 is the name of the lander, and Zhurong is the name of the rover. And this is a picture from the surface of Mars taken by the rover, taken of the rover. That's the little rover there with the two little eyes. And that's on the surface of Mars right now. So we need to understand that a lot of different countries are trying to understand what happened to Mars. Where did the water go? If there was water on its surface at one point in the past, where's that water now? Why isn't there life on Mars now? And the evidence is a little bit hard to understand. We can't go back in time on Mars. But I want you to think about the Earth for the time being. The Earth has a magnetic field. Inside its core, the molten iron is churning and creates the magnetic field that surrounds our planet, Earth. And that magnetic field provides protection against radiation from outer space. It keeps cosmic rays from hitting us. It blocks a lot of the storms that come off of the surface of the sun. Now we can see in this diagram, this is of the surface of Mars, these red and blue stripes tell scientists that at one time the surface of Mars was magnetized. So there must have been a magnetic field, but it's not there now. It disappeared. And we think that what happened is that Mars, because it's a smaller planet, eventually its core, its molten core, became so solidified that there was no more magnetic field being generated. And so that led to awful things happening on the surface of Mars. And in particular, it allowed the solar wind, the blast waves coming from the sun, to strip away the atmosphere that Mars once had. So Mars right now is a very cold, inhospitable place where the surface temperature is frigid. The atmosphere is very thin. There is radiation on the surface all the time coming from space. And we really don't think that life can exist on Mars right now at all. But the search there continues. How about elsewhere in our solar system? Oh, I want to say one more thing. The Europeans are going to launch a spacecraft, this rover, this is an artist picture of it, in 2028. It was supposed to launch this year, but it didn't. And this will be a spacecraft that will search specifically for life on Mars. So that's something that we can look forward to. And of course, we know that there's life on Mars because this astronomer discovered a Starbucks there. It's a little joke. I hope you enjoy it. Okay, how about elsewhere in our solar system? Venus is a planet very much like the Earth. It's roughly the same size. It has roughly the same mass, but it's very different. It has an atmosphere that you see there on the left that is almost entirely made of carbon dioxide. And that carbon dioxide, you know, on Earth, carbon dioxide leads to it's a greenhouse gas that leads to global warming. And on Venus, this has happened to an extreme. That's a picture of Venus on the right with the clouds removed, taken by radar. And the surface temperature of Venus is roughly nearly 500 degrees centigrade. It's almost 900 degrees Fahrenheit. And so it's not a place that we imagine would be very suitable for life at all. Here's a picture taken by a spacecraft from the Soviet Union of the surface of Venus. I'm sorry, I said 900 degrees Fahrenheit. It's more like 800, but still very, very hot. And so there's all this carbon dioxide. It's super hot. We don't expect life to live there. Well, how about farther away from the sun, outside Mars? Jupiter itself is a huge planet. It's very prominent right now in the east after sunset. I hope you all get a chance to see Jupiter. It's that really bright star in the east. You can't mistake it. But that's actually the planet Jupiter. And Jupiter is surrounded by some large satellites. You see two of them here, and this one is called Europa. Europa is very interesting because its surface is not rocky. It's actually covered with water ice. There's a rocky core, but then it's surrounded by a shell of ice, of water ice. And scientists believe that underneath the exterior, there's an ocean that covers the entire moon. And inside that ocean, who knows what's there? We don't know what the composition is of this ocean. We hope to find out maybe not too long from now. NASA is building a spacecraft called the Europa Clipper that will be launched next year and arrive in 2026. We hope to learn much more about Europa and whether it can possibly, in that ocean, just like on the Earth, whether there are situations that would be suitable for developing life. Going farther out, Saturn, the beautiful planet Saturn, also visible in the evening sky right now. When it gets dark, look to the south, look about halfway up in the sky, and you'll see a star that's pretty much all by itself there. That's the planet Saturn. Saturn also has large moons, and in particular, this moon, Enceladus, looks like this. It also has an icy shell on the outside and a global ocean underneath. And we've seen from Europa, from Enceladus, that there are jets of water shooting out into space that are heated underneath its surface. So this is maybe what's happening underneath the shell, the exterior of Enceladus. There might be a source of heat, just like we see on the floors of Earth's oceans, that is driving heat into this water and also driving gas, maybe hydrogen and methane. We know very little about this process. This is just a guess, but it's a very tantalizing guess because this is very much like the conditions that we have seen on the Earth on the floor of our oceans. Titan is a moon of Saturn. It's unusual because it has an atmosphere that is very dense in nitrogen, just like our atmosphere is mostly nitrogen. But it's also a very cold it's hard to imagine life being there. This is actually from a spacecraft that landed on Titan in 2005. We really don't expect any life on Titan. Okay, so those are the best candidates in our solar system. Let's go farther away. Let's go to other stars and imagine what life might exist there. Now, we have very few ways to actually see planets around other stars. So instead, we rely on telescopes to show us maybe where those planets are forming. Here is the constellation Orion. It's very pretty. Many people know what it looks like. It's got the 3 stars in its belt, and here is a bunch of stars that we say are the sword of Orion. And in the middle of that sword is a bright, this is taken in infrared light, a bright nebula, a giant cloud of gas and dust that is very dense and in places very hot. This is a place in space, not that far from us, where hundreds of new stars are forming right now. And this is what, when we look at that cloud with the Hubble Space Telescope, we see these are like little embryos of just the very first baby pictures, if you will, of stars and maybe their solar systems. And so we know that this process works, but it's because they're so far away, these stars may have planets around them, and it's very hard to see those planets. These 5 ways describe how astronomers can look for planets. Maybe they can watch them directly, but or maybe they can sense them in some other way. But the most successful technique is what we call transits, and I'll show you what that's like. It's the end of summer now, but earlier, or maybe now even, imagine you're sitting outside and it's a lovely evening and there's a light on over your head. And you're sitting there just watching the night, maybe talking, maybe listening to music, whatever. And you notice a little flicker of the light, and there's kind of a shadow in front of you. And you look up, and there's a big moth that's crossed in front of the light bulb. Now, you weren't actually looking at the moth, but you saw that the light shining on the porch flickered for just a minute. That's what a transit is like. Now, it turns out that moth and that light bulb, it doesn't matter if it's 2 meters away from you or 2,000 meters away from you. The amount of light that the moth covers, the bug covers, is going to remain the same. So astronomers use this technique to study stars and watch and wait for them to flicker, for them to dim in their light. If there is a planet crossing in front of a star, the total amount of light that we see from that star is going to drop very, very predictably. Sometimes, the shape of that dip in the light tells us a lot, whether it's a big planet in front of a small star or a small planet in front of a big star. And so we have launched a spacecraft, NASA did, this is now 15 years ago, to watch stars just to study, to see if they flicker, if their light flickers, which would signal that there's a planet going around that star. This is the area that was studied. This is a very rich area, almost directly overhead now when it gets dark. This star Vega, when the sun goes down, it's almost directly over your head. And this is the area that Kepler studied. And I won't tell you a lot of the details, but the bottom line is that Kepler discovered thousands of planets around other stars just by watching for these dips in the light. And here in this plot, this is the orbital period, how long it takes that planet to go around its star. Now, the Earth is 365 days, right? So we're about here. Here's Earth. Lots of these planets are very close to their stars. Look how short these periods are, just maybe 10 days. And in that case, the planet has to be so close to its star that it's just going around. A year on this planet is like 5 days long. And it's going to be a very, very hot planet, not the kind of planet that we would expect to have life. We call that a hot Jupiter. But some of the planets that Kepler discovered are very much like the Earth, at least in terms of size. That's really about all we know of them. We don't know what their composition is. We don't know whether there's water on the surface. All we know is that they're roughly the same size as the Earth. And it turns out that we have found, I'm going to skip. It turns out that we have found a lot of these planets in what is called the habitable zone of that star. So here's the thing. Some stars are really, really hot, much hotter than the sun. And some stars are cooler than the sun. I mean, they're still hot, but they're not as hot as the sun. And there's a point as you go outward from that star when the temperature is just right for liquid water. We're very lucky here on Earth because we're in that zone, in that green zone that you see there, called the habitable zone for that star. And so what Kepler was trying to determine, in addition to discovering lots of planets, is which ones are actually in the habitable zones. Not too hot, not too cold, just right for water around their stars. And you can see here, this is just a plot. It's a few years old now, but all of these objects here are in the habitable zones of their star. This means that on these planets, the temperature is just right to have liquid water on the surface. Now, we've gone beyond Kepler. NASA launched this spacecraft about 6 or 7 years ago, and it is looking specifically for planets like the Earth that are relatively close by so that we can study them. This is just a painting. This isn't the real planet, but it's discovered a bunch of these Earth-like planets around stars that are quite close to us. And that gives us a chance to try to study the planet. You know, astronomers don't just take pictures. They use also a technique called spectroscopy. And spectroscopy takes the light that's coming from a star or a planet and spreads it out into the rainbow. You all know what a rainbow is. It's when you take sunlight and you spread it out into red, yellow, green, blue, and violet. And the same way, we can take light from another star and spread it out. And sometimes that light, this is a portion of the spectrum that's at infrared. Think heat. This is in the infrared part of the spectrum. And there are certain molecules that we can tell exist on as far away as a different planet only by the way that they absorb certain wavelengths of light. It's a little complicated, but it's a way to remotely identify sort of the fingerprint of the atmosphere to tell what gases are in that atmosphere. This spectroscopy technique also allows us maybe to determine some of the elements of life. So this is a picture of the Earth, for example, taken in infrared light. This is not the light that we can see with our eye, but it's a different part of the wave of the spectrum. And it turns out that the way the light reflects off of the surface in the infrared tells us a lot about what is there. And so in principle, we can tell the difference between a surface that's covered with coral versus trees versus algae. These spectra are very powerful. And so one of the goals of the James Webb Space Telescope is to actually make observations of planets as they're crossing in front of their stars to see how the atmosphere of the planet might be affecting the light from the star. And so here's the Webb telescope. It was launched just last December, on Christmas Day, last December. And it's already, let's see if I have that picture. Here we go. It's already taken pictures, taken spectra, excuse me, of other planets around stars and determined, in this particular case, this is the designation for this planet. WASP stands for Wide Angle Search for Planets. And this particular planet is 1,100 light years away from us. But in the spectrum of its atmosphere, the Webb Space Telescope has already discovered that here is an atmosphere that has lots of water in it. So this is one of the big goals for the Webb Space Telescope, is to study other planets, to study the planets of these other stars. There are other big plans for telescopes in our world that can study other planets. This is a plan for a 30-meter telescope, maybe atop a mountain in Hawaii. Here's one that's being built in Europe right now. These will all be used to study planets. Maybe we'll even send spacecraft into space that can study these planets. You know, they're very difficult to actually see. And maybe by blocking the light from the star, we'll be able to see planets around it. That's what that proposal is about. Okay, so the search for life is just getting started. We're looking for planets that look like Earth. We're looking for planets that have atmospheres that maybe can have water in them or oxygen in them. It's going to be a challenge, but in the next 10 years, we'll make a great deal of progress on that. But why should we have to let science do it? Why not let science fiction do it? And you know, there have been a lot of portrayals of aliens in space movies and television shows over the years. And, you know, there is some possibility that there is life elsewhere that is trying to communicate with us right now. And this man, Frank Drake, was one of the pioneers of this study, this search for extraterrestrial intelligence, or SETI, S-E-T-I. And he came up with this equation that you see on the board. By the way, Frank Drake died, unfortunately. He was more than 90 years old just a couple of months ago, and we're really sad that he's gone. But he left us with this equation, and a very long time ago, he actually conducted an experiment to try to listen for a broadcast from another star system. That was his first famous experiment. And then he came up with this formula. And in this formula, the letter N stands for the number of civilizations in our galaxy, the Milky Way, that have radio communication, that are capable of contacting Earth. And what Drake did was he came up with the variables, the parts of this equation that you need to answer in order to figure out what N is. Now, we haven't gotten very far, but we do have a pretty good understanding of how often stars form in our galaxy and what fraction of those stars have planets. And then we're getting to the point that we can understand how many of those planets could support life. Is there water? Is there an atmosphere? So, you know, maybe there's a planet out there that's very much like Earth. Maybe there's a planet out there with an alien civilization that is broadcasting to all space around it that we're here, we're an intelligent species, and we live on this particular planet. So there are some studies that are going on now to try to find those communications, to listen, literally listen to outer space to see if there is a signal coming from another planet. Now, unfortunately, one of the best tools that we had for that search, the Arecibo radio telescope in Puerto Rico, collapsed and has been destroyed. So the answer here so far is we've done all these studies, but we haven't found anything yet. And so, you know, this search for life goes on. It's a question. Is there life elsewhere? Are we alone? That has been asked for thousands of years. Here's a quote from an ancient Greek philosopher named Epicurus, who said you can read it there. In English, it's, there are finite worlds both like and unlike this world. And so we must believe that in all worlds, there are living creatures and plants that we see here in our world. And in particular, in the 16th century, there was a Catholic priest named Giordano Bruno who said, he was really controversial, that he said there are countless suns and countless earths, all rotating around their suns just the way as we see in our solar system. And for this and other reasons, he was declared a heretic and burned at the stake. But he was right in the sense that to this date, right now, as of now, we know of more than 5,000 planets around other stars. Many of those planets exist in multiple planet systems. And so if you take the statistics of how often we are finding planets around other stars, and if you count the number of stars that we have in our galaxy, in the Milky Way galaxy, maybe 200 billion stars, and you work all that out, then there could be billions, many billions of habitable planets out there waiting to be explored and waiting to be discovered. And I want you to remember that just because a planet is habitable, just because it has the conditions that are right to develop life, that are the right conditions, you know, atmosphere and water and all that, that doesn't guarantee that life will develop. So we'll just have to see what happens. And I want to thank you for inviting me to your festival. And I think now we will have some questions.
Profesor Kaku, bienvenido.
El placer es mío.
Muchas gracias por venir.
Thank you very much, Kelly. Am I all live? Yes, I am. But you know the Zoom world, right? Gracias a amigos por acompañarnos. Gracias, Kelly, por acompañarnos. Y tenemos unos saludos. Parece ser que tienes unos fans ya aquí en México, Kelly. We have some greetings from some fan of you. Magdalena Rodríguez saluda. Cintia Delgadillo también manda saludos. Daniela Lomendí. Gracias, Daniela. Por cierto, Daniela va a dar una plática la siguiente semana. By the way, Daniela is going to bring a talk quite interesting. So I will invite you, Kelly, to join us also. José Luis Arreola, el profesor José Luis Arreola, nos saluda. Juan Pablo Martín también, Juan Salvador. Tenemos saludos de Alejandro Mercado y de Perla. Y vamos a pasar algunas preguntas. I'm gonna read some questions, Kelly, for you. Voy a leer unas preguntas que nos han compartido en las redes de Tribu y por mensajes aquí al WhatsApp en directo. Y tenemos una pregunta. We have a question for you, Kelly, from Antonio Limón, de Antonio Limón. Y pregunta, ¿cuántos años cree que falten para encontrar vida extraterrestre y cómo cree que sea? How many years do you think it lasts already to find extraterrestrial life? And how do you think that extraterrestrial life should look like?
Right. So, Antonio, it's a great question.
Antonio, Kelly nos dice que es una muy buena pregunta.
We now are developing technology that allows us to study the planets of other stars better than we've ever been able to do.
Ahora estamos desarrollando tecnología que nos permite estudiar planeta alrededor de otras estrellas mejor de lo que ha sucedido en la antigüedad.
You know, just 30 years ago, we weren't sure whether there were planets around any other stars.
Tan solo hace 30 años no sabíamos si había planetas alrededor de otras estrellas.
So now that we have discovered many of them, we want to try to study those planets, and that is a difficult task.
Ahora que hemos encontrado algunos de ellos, tenemos que decidir qué planetas estudiar y ese es un camino bastante complicado.
But we have an important new tool, and that is the Webb Space Telescope.
Pero tenemos una herramienta nueva muy importante y eso es el telescopio James Webb,
which can look in a part of the spectrum that is infrared light, not visible light like we see with our eyes, but longer wavelengths, kind of like heat radiation.
que puede observar en una parte del espectro, algo que Kelly mencionó en su charla, muy concreta, que es la luz infrarroja. No la luz que nosotros observamos con nuestros ojos, pero un segmento diferente de luz.
And it turns out that many of the important molecules in the development of life, water, carbon dioxide, methane, and other carbon compounds, express themselves in these wavelengths, in these infrared wavelengths.
Wow. Y resulta que algunas biomoléculas importantes para la vida, como agua, dióxido de carbono o metano, se expresan en estas ondas que el James Webb puede captar.
And so, for example, the Webb telescope has an important objective to study other planets and to try to determine which of them have Earth-like conditions.
Y de hecho, bueno, y ahí ya cancelamos dos preguntas que nos llegaron. El telescopio James Webb tiene, uno de sus objetivos es precisamente encontrar otros planetas con condiciones semejantes a las de la Tierra.
Now, it might be that Webb doesn't discover life.
Puede ser que James Webb no descubra vida,
but it can find planets where life could exist.
pero puede encontrar planetas en los cuales la vida pudiese existir.
Sometimes there is evidence that indicates life, even though you've not actually detected it.
En ocasiones hay evidencia que indica que ahí podría haber vida, aun cuando no se encuentre vida.
And I'll give you an example. Our planet Earth,
Nuestro planeta Tierra,
if seen from a great distance away, we wouldn't be able to detect life.
si fuese visto de muy lejos, no se podría detectar vida en él.
But we could detect that in our atmosphere, we have both oxygen and methane.
Pero se podría detectar que en nuestra atmósfera estarían presentes el oxígeno y el metano.
Now, these two gases want to combine very, very fast. So there should not be any methane in our atmosphere.
Y estos gases quieren combinarse de manera muy intensa, entonces no debería haber metano en nuestra atmósfera.
So the only way there can be methane in our atmosphere is if something is putting more methane in all the time, and that is life.
Así que la única manera que puede haber metano en nuestra atmósfera es que algo vivo la esté agregando a la atmósfera, y así es como se descubre la vida.
So I think, Antonio, that perhaps within 10 years, we will find planets with this kind of evidence that argues very strongly that there must be life on that planet.
Así, Antonio, que creo que, y hablo en nombre de Kelly, que tal vez dentro de 10 años se puedan encontrar planetas con estas condiciones en las cuales pudiese existir vida.
We might not be able to tell what kind of life it is, but we can make a guess.
Tal vez no podamos decir qué tipo de vida es, pero podríamos, take a guess, pero podríamos imaginarlo.
My opinion is that it is very probable that there are many other planets that contain microscopic life.
Wait for this. This is awesome. Y en opinión de Kelly, es muy probable que haya otros planetas en los cuales pueda existir vida microscópica. Wow.
But I don't think it will be very likely to discover another planet with intelligent technological civilization like us.
Pero en la opinión de Kelly, no considera que sea probable encontrar otro planeta con vida inteligente en las condiciones como nuestro planeta que habitamos.
And Antonio, let me leave you with this thought. Imagine that the Earth were completely covered with water and evolved exactly the same way, except it's all covered with water.
Ahora, Antonio, déjame dejarte con esta reflexión. Imagínate que el planeta Tierra esté cubierto por completo de agua y haya evolucionado en él el mismo tipo de vida.
Then what would the most intelligent life on our planet be? It would be
Entonces, ¿cuál
dolphins.
sería la vida más inteligente en ese planeta?
It would be dolphins and whales.
Serían los delfines y las ballenas,
They're very intelligent,
que son muy inteligentes,
but they're never going to build a rocket ship.
pero al parecer nunca van a construir una nave espacial.
They're never going to send radio beacons to another planet.
Parece que nunca van a enviar señales de radio a otro planeta.
So if we were studying the Earth from a very great distance, we might not know that they exist here.
Así que estudiando al planeta Tierra desde muy lejos, podría no detectarse vida en él,
But they do.
pero habría. Quite interesting, thank you. And actually, we have 7 questions, but I don't want to take much of your time, Kelly. So that may lead us to a question from actually Profesor José Luis Arreola. Voy a saltarme a una pregunta relacionada del profesor José Luis Arreola, que menciona si ha habido una modificación a la ecuación de Drake desde que Drake la postuló hasta la actualidad. Have there been any modification on Drake's equation since it was postulated until today?
No, the parameters of the equation are the same.
Los parámetros de la ecuación son los mismos.
And we are trying to get estimates that are somewhat accurate for each of them.
Y estamos tratando de encontrar aproximaciones más detalladas para cada una de estas variables.
So for example, we can estimate pretty well now how often stars form in our galaxy.
Por ejemplo, el día de hoy podemos conocer muy bien la tasa de formación de estrellas en la galaxia.
But we cannot estimate how often life will evolve into a technological civilization.
Pero no podemos conocer qué tan frecuente la vida evolucionará de una manera tecnológica.
And also, muy importante, we can't estimate how long that civilization will last.
Y también, y algo muy importante, no podemos saber qué tanto esta vida perdurará.
For example, here on Earth, we've had electronics for, 100, 150 years.
Por ejemplo, en la Tierra hemos tenido aparatos electrónicos desde más o menos hace 150 años.
And I don't want this to happen, but suppose there is a nuclear war and all of humankind is killed.
Y ojalá que esto no suceda, pero imaginemos que hubiese una guerra nuclear y todo esto perezca.
So then the lifetime of our civilization, our technological civilization, is only 150 years, not 10 million.
Así que entonces el periodo de vida civilizada sería solo de 150 años y no de 10 millones de años.
So this is one of the components of the Drake equation that will take a very long time to answer.
Actually. Así que este es uno de los componentes o de las variables en la ecuación de Drake que todavía no conocemos. Thank you very much for your answer, Kelly. Muchas gracias por su respuesta. Y si me permite, quiero leer también. Ok, esta me gustó mucho. This one, I find it quite useful. It's from Paulina, pregunta a Paulina. Una recomendación de un libro para comenzar a leer acerca de astrobiología. Do you have any suggestion about a book for astrobiology for beginners?
Ooh.
Kelly dice,
Paulina, there are many books that try to convince you that life is common everywhere.
Hay muchos libros que tratarán de convencerte que la vida es común en todos lados.
But there are not many books that talk about maybe life is unique to the earth.
Pero no hay muchos libros que hablen de cómo la vida es única en la Tierra.
One of the really good ones, it's about 20 years old now, is called Rare Earth.
Uno de los verdaderos libros interesantes que recomienda Kelly, que se publicó hace más o menos 20 años, habla sobre lo raro que es la Tierra.
And it is by two scientists who take a look at the special circumstances that make Earth a very unusual place.
Y fue escrito por dos científicos que hablan sobre lo inusual de las circunstancias que hicieron único al planeta Tierra.
And maybe those circumstances have allowed life to form here and it can't form anywhere else.
Y tal vez esas circunstancias permitieron la formación de vida aquí y no en otros lugares.
I'll give you just one example.
Te voy a dar un ejemplo.
On the Earth, we have a geology that causes plates of our crust to collide, and in the oceans, some plates go on top of each other. We call this plate tectonism or plate tectonics.
En la Tierra tenemos movimientos tectónicos que se refieren al movimiento de placas y algunas van debajo y algunas van arriba de otras.
And if it weren't for plate tectonism,
y si no fuera por el movimiento de placas,
think of what exists on the bottom of the ocean. Thick
piensa lo que existe
layers,
en el fondo del océano. Es una capa
thick layers of dead organisms, clams, and other seashells.
Es una capa de organismos muertos y conchas y otras estructuras marinas.
Those shells have captured a lot of the carbon dioxide that would otherwise be in our atmosphere.
Esas conchas han capturado mucho del dióxido de carbono que de otra manera estaría en la atmósfera.
But because of the moving plates, the ocean with the layers of sediment get pushed down deep into the earth.
Pero debido al movimiento de placas, esos sedimentos oceánicos se van hacia el fondo una vez que las placas se superponen.
And because of that, the carbon dioxide is removed and cannot go into the atmosphere.
Y gracias a eso, el dióxido de carbono se remueve y no puede ir hacia la atmósfera. I guess you're thinking of Venus, right, Kelly?
I'm sorry?
I guess you're referring to Venus.
Right. So if all of that carbon dioxide were actually in our atmosphere instead of buried inside our planet,
si todo ese dióxido de carbono estuviese en nuestra atmósfera en lugar de irse hacia el fondo de nuestro planeta,
the greenhouse effect would be extreme, and our atmosphere the temperature on the surface would be too hot to support life, just like on the planet Venus.
El efecto invernadero sería insoportable para permitir la vida, justo como sucede en el planeta Venus.
One other quick example. Our planet has a magnetic field that creates a protective sphere around our planet that protects us from radiation from space.
Nuestro planeta tiene un escudo de campo magnético que le protege de la radiación solar.
If it weren't for this magnetic sphere, a lot of the radiation would hit our planet, and that radiation is harmful to life. You can get a sunburn from too much ultraviolet light. Imagine getting too much cosmic rays and dying.
Imagínate que si afecta a la vida recibir mucha exposición al sol, imagínate recibir mucha radiación del sol. Esto causaría la muerte.
So these are two of the ideas that are discussed in this book, Rare Earth, and it talks about many of the things I have discussed, that what are the conditions that are good to develop life, and also some of the ways that Earth might be unique.
Así que estos son uno de los ejemplos que se mencionan en este libro de por qué los autores consideran que tal vez la vida sea única en el planeta. Kelly, could you please tell us the name of the writers? ¿Podrías darnos el
Yes,
nombre de los autores?
one of them is Donald Brownlee.
Donald Brown Lee.
Brownlee. Let me do it while we're talking here. Maybe we can get the next question and I will look it up.
Okay, never mind. Menciona Kelly que va a buscar el nombre mientras podemos leer la siguiente pregunta. Pero antes de leerla, y me parece
Peter Ward is the other author. Peter
what?
Ward and Donald Brownlee.
Peter what, sorry?
Ward, W-A-R-D.
Okay, Ward, thank you. Ok, son los nombres de los autores, los vamos a escribir más tarde al filo de este video en las redes, dado caso que alguien esté interesado en el libro. Ahora, antes de leer la siguiente pregunta, before I read maybe the last question, quiero decir algo a nuestro auditorio. I want to tell something to our audience. Hace 2 semanas, 2 weeks ago, estaba buscando sobre el curso de Sistema Solar del MIT. I was looking for the Solar System course from MIT. Y adivinen ustedes quién es el autor del libro de texto de astronomía del MIT. And guess who the author is of the textbook at MIT? Mr. Kelly Beatty, indeed.
Yes, indeed.
We admire you so far. Yes. Y por eso el honor y estamos tan contentos de que hoy nos acompañe. Espero que la siguiente vez que nos veamos, Kelly, poder llevar el libro para que nos lo puedas autografiar. I hope next time we meet to bring the book so you may autograph it.
It would be my great pleasure.
So I'm going to read maybe the last question, okay?
Okay.
I mean, we have 8, but most of them are quite similar. Tenemos varias preguntas, pero algunas de ellas se parecen. Y esta es interesante y pregunta, ¿podrías hablar un poquito más de la misión que la Agencia Espacial Europea va a enviar en el 2028? Could you please tell us a little bit more about the European mission 2028, please?
Yes, the Rosalind Franklin.
Sorry, what?
Rosalind Franklin is
La misión
a
Rosalind
rover.
Franklin.
Yes.
Okay.
Let me tell you who she was. There is when DNA was discovered, the 2 men who were the scientists got the Nobel Prize for that discovery.
Cuando descubrieron el DNA, hubo 2 hombres laureados con el premio por el descubrimiento de ese DNA.
But Rosalind Franklin was the laboratory technician who ran the X-ray crystallography equipment that was able to determine the structure of DNA.
Pero Rosalind Franklin era una técnica de laboratorio encargada de hacer el estudio de cristalografía que permitió ese descubrimiento.
So this lander, named for her, will actually search for life.
Así que este dispositivo nombrado en honor de ella va de hecho a buscar vida.
On the surface of Mars, maybe not existing life, but perhaps fossilized life.
Va a buscar vida en la superficie de Marte, tal vez no vida actual, pero vida fosilizada.
And how will we know that it was life and not just a bunch of organic molecules?
¿Y cómo vamos a saber si eso fue vida y no solo un montón de moléculas orgánicas?
Life is very clever. It uses the elements around it to create life most efficiently.
La vida es muy sagaz y utiliza moléculas alrededor de sí para crear vida de manera más eficiente.
So, for example, in our in life on Earth, you know there are 3 isotopes of the atom carbon: carbon 12, carbon 13, and carbon 14.
Okay, wait for this one. Así que en la Tierra existen isótopos de carbono específicos para la vida, como es el carbón 12, carbono 13 y carbono 14.
And life preferentially uses carbon 12 to make its structures because that is the simpler atom.
Y preferentemente la vida utiliza el carbono 12 para hacer estructuras porque es más simple.
So if you analyze a block of wood for the carbon,
Así
and
que
if
si
you
analizas
analyze
de madera para el carbón,
and if you analyze the carbon dioxide in our atmosphere,
y si analizas el dióxido de carbono en nuestra atmósfera,
the ratios of those isotopes are different.
los Las
The
concentraciones de esos
proportions,
isótopos,
the proportions of.
las concentraciones de esos isótopos son diferentes.
And so we know that the wood
Así que sabemos que la madera
was once alive.
alguna vez estuvo viva.
And so when we get to Mars, the spacecraft will do an analysis of, if it finds organic molecules, it will study these kinds of very subtle properties to determine if life once existed on Mars.
Ok, así que cuando este dispositivo llegue a Marte, va a analizar precisamente estas características para saber si alguna vez existió vida en Marte. Well, quite interesting, I must say. Kelly Beatty, it's been such an honor. Ha sido un honor, Kelly Beatty, contar contigo. Agradecemos mucho tu generosidad de tiempo. We thank you for your kindness and thank you very much, and clear skies for everyone. Y a todos, cielos despejados. Y gracias por acompañarnos en la primer charla del Festival de la Astronomía. Cielos despejados para todos.
Gracias.